Welcome everybody to the E3SM All Hands webinar. We're happy to have Luke Van Roekel join us today. Luke received a PhD from Colorado State in 2010. He joined DOE in Los Alamos in 2015, and now he's the group lead for the Omega Ocean team for Phase 3. And today he's going to be telling us about his ImPACTS SIDAC project, which just began this past year. Thanks, Luke.
All right, thanks, Mark. Let me get this in the slideshow. All right, well, I appreciate the opportunity to talk about the SIDAC project here. This is a pretty large effort amongst these institutions shown here at the bottom. It's a good team. We have a real nice breadth of Oscar-funded folks, computational scientists, all the way to domain scientists, and thankful to those who I see already on the call today from the team. So I'm going to give a very brief overview of some of the work we're doing, but first thought I'd start with an overview of the project itself. Many of us are well aware of this, but E3SM is a pretty well-known weak AMOC bias. So here on the left, a paper by Wilbert Wire and others shows this, that E3SM is the bottom of the CMIP6 envelope, but there is wide variability at this resolution. And so there's a lot of question of, is this model that gets it maybe exactly right, getting it for the right reason? Why are they overestimating? Why are we under? Complicating our story, we know that at high resolution, we do well. At low resolution, we're weak. So this is a figure from Peter Caldwell's paper on the V1 high res, where the coupled high res is very robust overturning, showing the weak at low res. So there seems to be something at play with resolution. So part of this is trying to understand AMOC, fix a bias, but in the process of we try to gain physical understanding. The second half of this is to really try and, for the first time, simulate a possible collapse at high resolution. So the AMOC, the Atlantic meridional overturning circulation, redistributes significant amounts of heat and salt. It's linked to many climate impacts. I list a few here, such as hurricanes and droughts. And a collapse of AMOC is projected to have extremely strong impacts, seen in the figure below, where you have regional expression of a collapse, something on the order of 8 degrees Celsius, with a global mean of around a degree or two. So it's an important thing to understand. For a very long time, back to Henry Stummel in the 1960s, AMOC has been theorized to be bistable, and this has been shown in many simplified models, box models, for example. Wilbert and Hank Dykstra and others showed this in an interesting, slightly more complex model that was an implicit model, and they showed there are two branches, a robust overturning state separated by an unstable attractor, and then a weak or off state. And this bistability is usually assessed through a metric called FOVS, which is the freshwater transport at 34 degrees south into or out of the Atlantic. And a negative FOV is thought associated with a bistable AMOC and a positive monostable. So had some recent analysis by a visitor here, Renee Van Westen, out of Utrecht University, showing CMIP6 models, their FOV along the bottom and their AMOC strength. And they follow pretty nicely along a line where a stronger FOV, a more positive FOV, seems to be associated with more positive overturning. For example, in the CESM high res and low res, you can see here, E3SM is on the low side, but intriguingly fits on this line as well. We tend to have a negative FOV. So one thing we're doing well is we got FOV correct. The observational range here is shown in these pale yellow, but the observations are actually up here, where this is actually reanalysis, so not quite observations. So what could happen is if you could increase the freshwater transport into the Atlantic, you may slide rightward on this graph and potentially up in overturning. So with that background in mind, our goals here in this project are really to understand the weak AMOC within E3SM and improve this representation. So we're tackling this in a number of ways. One is to leverage traditional oceanographic analyses, also trying to expand beyond things like rapid 26.5 north or just stream function plots, to also exploring some AI-based analysis, including trying to construct a neural network trained adjoint, which I'll talk about a little bit later. We're also interested in improving analysis capabilities of our code as well as other ocean models. So we want to improve not only our in-situ diagnostics, but we're contributing to a community AMOC package called Metric. We're also working on some new Lagrangian particle tracking capability for the possibility of long-term high-resolution configurations to use this capability. And like I said, at the very end, our goal is to try and assess AMOC stability at eddy resolving resolution, but this requires significant advances in spin-up capabilities and improvements in model performance. So we're spanning all the way across. So project team and structure, we are 8 institutions. On the project, we have a significant contribution from the SIDAC Rapids II Institute, and we're really well balanced, as I mentioned, between computational science, applied math, and domain science efforts. And right now, I've divided this project into 4 teams. One is conducting simulations and doing more oceanographic analyses. We have an adjoint team, which is working on building this neural network adjoint. There's an AI team, which is now combined with the Lagrangian particles team, and also performance as well. So a few highlights from each of these 4 teams. From the analysis folks, there's been some nice progress in designing new simulations. We have some unique simulations planned, such as starting from averaged state, not trying to bake in the AMOC, instead seeing if it emerges naturally. So if we have a hemispherically symmetric state, does it emerge on its own? We're also working on a lot of analysis. We're starting up on some water mass analyses. We're doing pathways of AMOC, like I said, FOV analyses, and then a systematic examination of stream functions. So what does our AMOC look like versus POP versus GFDL, these types of questions. We're also trying to keep an eye toward integrating this analysis for future use by E3SM. Our first example is in the bottom right, where we do have a version of MPAS analysis of FOVS that we're going to be integrating into the code for analysis in all E3SM runs. One specific example, I referenced this a little bit from a recent visitor, is a look at some water masses in a bit of a cursory way. So on the left panel, there are reanalyses here. On the right, this is from an E3SM simulation. It's called the SORM run, the Southern Ocean Regionally Refined. And what you'll notice is near the surface, through maybe about 600 meters, E3SM does pretty well at reproducing the structure, the velocity, and the salinity of reanalysis. But once we get into the Antarctic intermediate water layer, it disappears. So we lose this fresh signal such that we end up having a more negative FOV, like I pointed out previously. So this reduction in FOV, as I mentioned, could reduce AMOC. So if we were able to increase Antarctic intermediate water, and we're starting to think about that, I can circle back to this if people are interested, how we might construct a simulation that makes sure that's in there to test the sensitivity, which is ongoing right now. From the adjoint team, the main goal is to infer sensitivity of AMOC with respect to a large number of parameters that may have spatial variability, but with temporal invariance. So you would think of this as like the GM parameter for mesoscale eddies. What is the sensitivity of AMOC if you increase it in one region versus the other? This can be done in a couple of ways. First is a brute force type approach, where you could say, I'm just going to change it here, here, and here. But a more, say, robust way is to use an adjoint model, except for the difficulty here is that it's very hard to make these. It takes a lot of time. It takes a rebuilding of the code, essentially. So what we're exploring is to try and train a neural network adjoint based on MIT GCM, which has an adjoint already. And then using a new capability we're developing, we're pushing forward beyond some work done by Mark Peterson and a student, Robert Strauss at Los Alamos, to make this more robust so we can do some transfer learning to get the MIT GCM trained one into E3SM. What we hope to do is exploit differentiability of neural networks and of this Julia code so we can start to use auto differentiation instead of building our own adjoint model. And we're also exploring the use of this package Deep Hyper, which is a machine learning sort of design hyperparameter search. It examines different architectures developed in the Rapids 2 Institute, and it's also very performant on exascale resources. So right now what's being worked on is to explore what we can with CMIP6 data. This is difficult because parameter ensembles are not common. It's more structural differences with the same forcing and roughly the same parameters. But like I said, a new version of MPAS for some parametric ensembles. So this stacked shallow water or Julia version that exists right now, we can think of this as a pretty simplified version of MPAS Ocean. And right now, Stephen Bruce and others are working on adding vertical mixing and some other important processes such as temperature and salinity, nonlinear momentum advection. And once we get this to a place where we can, say, do a double gyre case, such as the simulating ocean mesoscale activity test case or SOMA within this code, we can start to use this to do adjoint sensitivity by differentiating with some commonly used Julia libraries such as Enzyme. So very, very early results that this team has conducted is using a Berger's equation model, a very, very simple case, and trying to say, what do I get if I train based on just the forward loss? What if I do it with just an adjoint sensitivity? And what if I do it with both? It's a little difficult to see, but you can obviously just the adjoint doesn't work. It looks pretty bad. But what you'll notice, hopefully, is that if you look at the color bar here on the predicted versus the true solution, we're overestimating values with just the forward model. But if we use both, we start to pick up the correct adjoint structure and we get the predicted solution correct. So we're showing a little bit of promise with the caveat that this is very, very rough and it's a very simple case. Skip that. So moving from there to the machine learning team, the main goal here is to develop some machine learning based surrogate models. What they really are after here in the project is to reconstruct climate fields from limited measurements. And here we can extend limited measurements from, say, observations to say, can I reproduce a full field from, say, low resolution data? So can I reconstruct high resolution variability, think like eddy-like structures from some machine learning based model and low resolution input data? So the first example they've done, they've taken some E3SM data and looked at global surface temperature. And on the left down here is the reference data of 2 meter temperature, I believe. And what they did is to withhold a large number of the points. I believe the number is about a half of the data is withheld. And they run it through their new machine learning methodology. And they're able to make a prediction or to fill in the gaps really nicely. So their prediction matches really well so far. So there's some promise here. Next steps are to fine tune this and do some further comparisons across different models in different cases. Another case that we're working on in the machine learning group is tensor factorizations. So how I like to think about tensor factorizations is they're somewhat of a generic EOF. So empirical orthogonal function, they can be used on higher dimensional data. But since these are different, one of our main tasks initially, actually, that's being led out of Los Alamos is to develop a write-up on what these things are and how they could be useful for earth science in sort of an educational sense. So we're trying to communicate to the community why these are important. So that's underway. We're also applying for the first time some graph-based techniques for tensor factorization. So this is not like structured cases where you have a time series at every point and you do principal component analysis across all the data. It's a little more complicated on unstructured meshes. So we're testing out some of these techniques for unstructured grids, such as we have for the ocean. And that is working for offline code, and starting to do some mode comparisons of these empirical orthogonal functions from different models. For example, here's some modes from GFDL on the left and CESM2 on the right. These are AMOC. We're also trying to figure out how different variables link together within the field. This is called maximal covariance analysis, of linking different modes together and finding dominant modes to try and untangle why AMOC might be stronger in one versus the other. The plans for this is to make this in situ, so we can do this on the fly in sort of a streaming tensor factorization approach, and do a more robust analysis of these unstructured models or graph-based decompositions against traditional EOFs with a newly developed comparison tool. The next effort I wanted to highlight is particle tracking. So within MPACTS right now, we do have a Lagrangian particle tracking capability, but it doesn't do everything we need in terms of having a robust long-term capability. It needs to be reset every so often. So imagine you seed some particles in your domain and you let them sort of wander around. Eventually, some of the particles are going to leave a given processor domain, and we can't have a complete domain go empty. So we need to figure out how to do this. We need to figure out how to do this efficiently, because it can be very, very complex to do this. You have to think about what velocities do I, if my Lagrangian particle, say, is in the middle of one of these hexagon cells, not quite in the middle, maybe it's on the side, what value do we take? And how do we efficiently get a velocity nearest to where the parcel path is at a given time? So shown here on this slide is actually some initial results from an MPACTS offline type run, where they're running these particles through right now in a bit of a toy model approach, but we're making good progress in this area as well. One way we're doing this to enable this long-term capability that we can use on exascale resources, a number of folks on the team highlighted here on the bottom, Hanqi Guo, Hanwei Shen, and Tom Paterka, have done some really nice work on exascale-enabled flow visualization and using reinforcement learning to being able to do this dynamic decomposition and to scale this up to exascale. So what we're able to then do is, with this technique, they've shown that they can scale particle tracking up to 16,000 processors with like a domain of 4,000 cubed. So very big problems here so far. To push this even further, what's being worked on is to change this common code, this OSU flow code, from CPU to GPU. So we can have this run independently and transmit model U and V and W every so often to let this thing just kind of go. And that's underway and making good progress as well. Of course, to do this at on big machines, you also need very efficient transfer between these components. So what we're exploring right now is a library developed out of Argonne. Tom Paterka is part of this Lo5 library, which allows for efficient transfers from, say, MPACTS Ocean, where we can pass mesh information and velocity, and it captured this on the fly, and it does this in-memory distributed data, sends the metadata, and pushes it out to OSU flow. We can also write to IO, but we don't need to. We can communicate directly. And right now, what has been done on that part of the team is they have a case now that's working with the Lo5 library where we can capture some of these MPI calls and have it reassign ranks on the fly. So they have a MPAS Ocean test case on a local machine that they're able to run and do this work on. Yeah. So moving to the definitely not least important, but one of the last team on the list, the performance team. This is a really nice collaboration between folks on our project at E3SM and the Exascale Computing project, and then with vendors like Cray and NVIDIA. So some work that's been done on Crusher at Oak Ridge shows that MPAS Ocean on the GPU side is about 7 times slower, but on other machines it's better. So this is shown at the bottom in this table. So CPU numbers across the top and then GPU across the bottom. You see, pretty bad. It's gotten quite a bit worse. So in some profile analysis, 3 kernels within the Ocean model really dominate the story. If you can read that, they're tracer advection. So there was work done to figure out why this is the case. And long story short, what was found was that when we have these thread private variables that are arrays, such as highlighted here, every single thread was making their own copy on every GPU. So this is like 3,000 copies of this. So this is taking a lot of time and a lot of memory. So that was removed and the code was restructured. And the payoff here is that we picked a factor of 3 in the time on GPU. So it went from 1 to 5 to about 58. So it's getting better. 2 versions are bit for bit. And further optimizations are being pursued. There are some similar cases, for example, in the vertical mix code. So progress to date, we've generated a lot of new analyses. We're working closely with the E3SM team, in particular the coupled model team, to look at the AMOC bias and try to make this better in time for V3. As I showed from Renee Van Westen, we're able to show possible new explanations for the weak AMOC and E3SM, and we're starting to look at how we might assess that in simulations. Some of our initial AI-based techniques and explorations are showing promise, especially in particular, like I mentioned, for injecting high-resolution variability into a lower resolution simulation. So this might be important for the spin-up problem where we can run low-res for a very long time. For the entire 1,000 years you might need to spin up the ocean, but we can't do that for high res. So potentially we could use this to make a high res that has that low res physics in it, but also the high res variability. We're also working on the particle code. We're porting to GPU. We're going to be adding new features like Argo float capability so we can have these particles go up and down to sample the water column as well. Right. We're also working on collaborations. Like I said, we collaborate with this university in the Netherlands. Next kind of steps are to start more runs. We've started some perturbed parameter simulations on some project resources. Like I said, we're working on this MPAS Julia code and then doing a reduced order cost perturbed physics ensemble. A lot of these machine learning techniques, the next step is to make them in situ, so to stream them. And on the performance side, we're working on some time stepping, finalizing the testing of the Adams Bashforth 2, and also continuing GPU work. So that is what I had. I'd be happy to take any questions.